Hi, everyone. So in this video, I'll talk a little bit about how to Eulerize a graph. All right, so we're looking at a graph here, and the idea is that this is a graph of a city block. And if you recall, we had this problem at the outset, which was how do we deal with a security guard that may want to uh, take a walk across city streets in sort of an efficient way. In other words, the security guard has two aims. They'd like to cover all of the blocks, so they'd like to walk, you know, through every single block, and they'd like to do it in such a way that they're not constantly retracing their steps, and going backwards. So the ideal situation here, of course, is if when you look at the map of the city and you make it into a graph, you have an Euler circuit on that graph. So how do we find out if we're in that ideal setting? Well, we look at all of the vertices and we ask whether or not they're even or not, even or odd. And if you don't recall what that means, let me go through it again. So we look at every single vertex, like a vertex here, and we ask how many edges are going out of that vertex. In this case, there are two edges, so we say the degree of that vertex is 2. And if the degree of a vertex is even, we call the vertex even. So this vertex on the corner, and in fact on every of those corners, is an even a vertex. If we look in the interior vertices here, they have 4 edges coming out of them, so they're also even. So all 4 of these guys are even vertices. On the other hand, when we look at an edge on the side, so either one of these vertices, we see 3 edges. When we look at one of the sides of the map and a vertex on that, we see 3 edges coming out. So we have a degree 3 vertex here, or well, we have several of them. And so those are odd. Now, when we see an odd vertex, we maybe become a little dismayed because we know by Euler's circuit theorem that there is no circuit for this graph. No Euler circuit, pardon me, for this graph. So what we do is we try to Eulerize it. And what does that mean? Well, what we're going to do is for each vertex that's odd, I'm going to make it red. So I'll just cover it with this red dot here. And that way I can kind of see quite clearly which vertices are odd and which are even. The even ones I'll leave black. And then the idea is going to be, well, we don't have an Euler circuit now. We'll adjust our graph by adding some edges so that we do have an Euler circuit in the new graph. And how do we want to adjust our graph? Well, we'd like this to still be a graph that makes sense with our map. So we don't want to, we're not going to go and take a bulldozer and make new roads for our security guard. Instead, we're going to just duplicate edges. So we're going to try to duplicate any edges between 2 odd vertices, if they exist. Vertices. So what that looks like, what that'll look like is we're going to take this edge and duplicate it. We'll take this edge and duplicate it. And we'll take this edge and duplicate it. And we'll take this last edge here and duplicate it. So here what we've done is we've duplicated 4 of the edges. And one way you think is you're just making a multiple edge on each of those 4 edges. And now we can take a look, and if we look at this vertex here in the new graph, in the Eulerized graph, this is called the Eulerized graph, we can ask what's the degree now of these previously odd vertices. Well, we've added one edge to each of them. And so we've gone from an odd to an even vertex. And now we haven't added any edges incident to the previously even vertices. So now every vertex is even. And Euler's theorem says that there is an Euler circuit here. And you can go through Fleury's algorithm to find it, or find one of them. And while that path for the security guard is going to retrace some steps or some blocks for the security guard, you can actually see exactly how many, right? There are exactly 4 blocks that the security guard will have to go over again if they want to, visit every block once, or well, visit every block sort of a minimal number of times. Okay, so this is a nice solution to this original problem, street routing problem that we had. There was another street routing problem, which was this sort of postal carrier. So I've drawn another map that's, these are simplified versions of what we started with. And again, what we want to do is the same thing. So if you recall that this is the mail carrier problem, and really what you're supposed to imagine is that there's one road between these guys, but the mail carrier needs to walk on one side of the street and the other side of the street to drop off all the mail. So what you do is you turn all of those roads into multiple edges, and now you want to again find an Euler circuit if it exists, and you again go through this process where you look for the odd vertices. Okay, so we've got an odd vertex here. We've got an odd vertex here. We've got an odd vertex here and here. And we've got one more odd vertex, I believe, and it's right down here. And if you look at all of the others, all of these interior ones, they have degree 8 now, because we've doubled all of the 4 edges. This has degree 4. This has degree 4. These two, oh, it looks like I did miss one. There is one right here, pardon me. This one has degree 4, and this one has degree 2. And I should have noticed that that I missed one because we should always only have an even number of odd vertices. And there was only 5 before, now there's 6. All right, so now we'd like to Eulerize this graph. And what I said before, we're going to all of a sudden realize maybe we have an issue. So now we want to duplicate edges between 2 odd vertices. That's what I said to do up here. However, if we look, we see we really can't do that here because there's only one odd vertex here, and if we duplicate, if we put an edge here, what would happen? Well, let's see what would happen. So let's say I put an edge here. All right. Well, now I've fixed that odd vertex so it's even, but I've made this vertex odd. Now it has degree 5 where it had degree 4 before. So what I've done is I've sort of moved the red down, moved my red vertex and created another red vertex. So when you're in this kind of situation, you have to add multiple edges in order to, in other words, what you have to do is you have to find a path from one odd vertex to another. And ideally, you'd like to find a collection of such paths so you minimize their length. In other words, you're not creating more edges than you have to. So in this case, we could do the following thing. We could create a path, not just add a single edge, but rather a path here. And now, because we added one coming into an even and another one going out, we've added two to that even, and so it's still even. But we've gotten rid of the oddness of these two vertices. So now we still have these guys, but so what are we going to do? So for those guys, well, we can certainly just we can duplicate the edge here. That's good. Now we have those even. So all of these guys are even. And that just leaves these two odd vertices here. So we need a path from one to the other. And you can see that any path, I mean, the shortest path that we can get is still going to be of length 1, 2, 3, 4. So we're going to have to add 4 there to get all the way. And so we do that. You can add any 4 you want. If you want to be maybe as simple as possible, you can just add them along the edge here. Okay, so we added a path between any 2 of the odd vertices. We tried to find the shortest one that we could. And remember, short doesn't mean um, distance. It means the number of edges. So the length of a path is the number of edges in that path. So now we have an Euler graph. We have a graph that has an Euler circuit, and we can find that Euler circuit by Fleury's method, Fleury's algorithm, and then know how many times the postal carrier has to repeat their steps. All right, so that's that kind of a problem. Of course, what we were just doing was called Eulerizing a graph. This is all Eulerizing. There's a semi-Eulerizing method. And all that means is that we're not interested in finding an Euler circuit, but rather an Euler path. And so let's see how that would work. Let me give myself my template here. Okay, so again, I'll look at a graph like this, and I would want to find the odd vertices. And you can actually look and see that there are a bunch of them. I'll just try to fill them all in. Shouldn't take too long. And here again, you count the number, you count the degree, or you calculate the degree by counting edges. And once you have it, then you can see whether that number is odd or even, and that tells us whether we have an odd or even vertex. Okay, so let's see here. I've got 2, 4, 6, 8. Okay, I have an even number of them, and I believe these red ones are all of the odd vertices. And semi-Eulerizing is really just you're going to pick a starting vertex, and you're going to pick an ending vertex. Okay, and well, let me pick actually slightly differently. I'll pick a start here and an end here for convenience sake. And once you do that, you apply Euler's theorem for paths, and you ask the question, can I start at my starting point and end at my ending point? Well, the only way you can do that and get an Euler path is if those 2 vertices are odd and every single other vertex is even. So these guys have to be even, and everything, and the start and end have to be odd. And again, the way you deal with that is you just go ahead and add the you duplicate the edges if they exist that just connect um, to odds. Um, great. So we can just duplicate that, duplicate here, and more duplication. So if you add those edges, you multiply those edges, you now have a graph that has an Euler path from the start to the end. It could be the case, of course, in this example, I had a start and an end that were both odd. However, I could have had the same kind of a problem, but I could have said, well, actually, what I really want to do is I really want to start here. I want to start up at this guy. So if you want to start here, then you really have a different kind of a problem. You know from Euler's theorem for paths, for Euler paths, that if your starting vertex has to be odd and it's even, which means you can turn it into an odd if you add another edge, and then you can turn this neighboring guy into an even because it's not where you want to start and end, uh, in the same swoop, in the same fell swoop. So you just do that by adding that edge there. And now we have an Euler path. All right. So this method that we're looking at here in this video is called Eulerizing a graph. It solves several of the street routing problems. The bridges problems also can be solved, solved as in giving the most efficient kind of path using this method. All right.